In the earlier recorded lecture, the equations that are used to calculate the rate of heat transfer in a substance were derived. The actual geometry of a body, subjected to heat transfer processes, may be simplified into one of three basic model of heat transfer system, that will be used throughout the course. We will refer the heat transfer system as the large plane wall, long cylinder, and sphere. You will find that I will be using the same engineering model when dealing with other heat transfer topics. In this lecture I will demonstrate the heat transfer approach to model the actual body, and solve a prescribed engineering problem. We will consider an egg, which has a complex geometry, and we can only approximate its shape. We will place the egg in a boiling water or in environment in which the temperature of fluid surrounding the egg is 100 degrees Celsius. Inside the egg is the yolk, and we assume that the yolk is perfectly attached to the internal surfaces of the egg shell. We will assume that the internal shell temperature is at 80 degrees Celsius. The engineering problem is to determine the rate of heat transfer across the egg shell. Now, I have never teach you how to calculate the rate of heat transfer through the egg shell, because the egg shell is neither look like a plane wall, long cylinder, nor a sphere. But we will approximate the shell as plane wall. The engineering assumption may not suitable for the whole geometry of the egg, but it is interesting to know how good is the geometrical simplification. The assumption may be appropriate if the thickness of the shell is significantly thin, when compared to the radius of curvature of the shell. The calculation may not be accurate for the whole domain, but provide good result at certain location on the egg shell. The online information shown in the clip tell us the range of eggshell thickness between 0.24 to 0.42 millimeter. In this exercise, we will assume that the thickness of the eggshell to be 0.24 millimeter. So when we say the eggshell can be modeled as a large plane wall, it comes with engineering assumptions, that the heat flows steadily and one-dimensional in the substance, the rate of heat transfer and properties of the heat transfer system are constant. Important concepts are shown in the clip. The temperature difference is -20 degrees Celsius, the thickness of the shell 0.24 times 10 to power of -3 meter. The origin of coordinate system is placed at which the external surface of the eggshell is 100 degrees Celsius. In order to us to calculate the rate of heat transfer, we need information about the heat transfer area. Right now we have difficulties to evaluate the heat transfer area, and we will solve the issue little bit later. Another property that we need to know is the thermal conductivity of the shell. I have done the online search, and you may find the information from the ResearchGate, a web portal that researchers use to share their research findings. I am using such information, and the thermal conductivity was 0.456 watt per meter Kelvin. The low value of thermal conductivity implies that eggshell has reasonably high resistance to heat flow, or we can say that the shell allow low rate of heat transfer through it. The thermal conductivity at room temperature for various material is shown in the clip, and according to the chart, the thermal conductivity of eggshell is in the range of that of an insulator material. On the issue of heat transfer surface, I decided to consider a small eggshell area. I consider the heat to flow into 1 mm x 1 mm cross-sectional area. The three-dimensional model of heat penetration volume is shown in the CAD drawing, as a rectangular cylindrical hole through the shell. By taking a small region, we can calculate the rate of heat transfer, and make comparisons with that flow into other geometries. Let us take the heat transfer area of 1 mm height and 1 mm width. Now the information about the properties is shown in the clip: the temperature differences, the thickness, the heat transfer area with 1 mm in z direction and 1 mm in y direction, and this give 1 times 10 to power of -6 meters square. Then we have the thermal conductivity, that we assume constant in the eggshell. With this information I wrote the equation, to calculate the rate of conduction heat transfer, in term of temperature difference, with negative in the right-hand term to satisfy the second law of thermodynamics. I used the Desmos scientific calculator, an online calculator, and placed all the information in the input field to calculate the rate of heat transfer. The calculator give us 0.038 watt for a heat transfer area of 1 mm height and 1 mm width. Now we are going to model the eggshell as a long cylinder. Remember that the heat transfer area change with radius, r. We need to define the heat transfer area, in the Fourier law of conduction, for a long cylinder. We will use the same heat transfer approach with that of the large plane wall. We will consider a portion of height, of the cylinder. To be consistent, we will take 1 mm height along the vertical axis or z-axis of the cylinder. The three-dimensional representation of heat penetration volume through the eggshell is shown in the CAD drawing. The Fourier law of conduction for long cylinder is shown in the clip. For steady one-dimensional heat flow along the radii direction, it is assumed that the rate of heat transfer and thermal conductivity take constant value. H is the height of cylinder. The rate equation require the value of an unknown geometrical property, the radius of the eggshell. The online information about egg measurements is shown in the clip, and we will take the chicken egg with diameter of 43 mm. Using the Desmos scientific calculator, we can then use the inner and outer radii of the long cylinder. The radius of cylinder at which the surface temperature is 100 degrees Celsius is 0.0215 meter, and that at which the surface temperature is 80 degrees Celsius is 0.02126 meter. The equation to calculate the rate of heat transfer is written in terms of temperature difference, defined as cold minus hot temperatures, with the negative sign on the right-hand side to satisfy the second law of thermodynamics. The information of heat transfer properties is placed at the input field of the calculator, and the rate of heat transfer is -5.105 watt. Comparison with the large plane wall case, we can observe two main differences. The rate of heat transfer for long cylinder take negative value, and the magnitude of heat transfer rate is much larger. Next we will model the eggshell as sphere. The spherical shape approximate the eggshell geometry much better than that of the long cylinder or plane wall. the rate of heat transfer will be calculated using that derived for sphere. The Fourier law of conduction for the heat transfer system is shown in the clip, and its general form is exactly similar with that of long cylinder. The equation to calculate the rate of heat transfer through a spherical shell is written in term of temperature difference Tc minus Th, to represent the heat flow, with the negative sign to quantify the second law of thermodynamics, and the radial coordinates of cold and hot surface temperatures, Rc and Rh. The equation is not in the same form as appear in the reference book, because I want to maintain the functional relationship between the rate of heat transfer, temperature difference, and the direction of heat flow from radial location of hot surface Rh, to cold surface Rc. Using the Desmos scientific calculator, I placed all the values in the input field as shown in the clip. The calculated values for the rate of heat transfer through the spherical shell is minus 218.271 watt. The values for heat flow through plane walls, long cylindrical and sphere models are compared in the clip. The equations are all written in the same form, in terms of its functional relationship of temperature difference and direction of heat flow. We can observe two differences. The rate of heat transfer is obviously different between one another. There are negative values for long cylinder and sphere. It is interesting to know why such observations can occur, and how it appear in the calculation. When we look at the origin of the equation, for plane wall, the origin of coordinate system is placed at the hot temperature surfaces. However, for the long cylinder and sphere, the origin is defined at the center line and center point respectively. It is appeared that the hot surface temperature is located at the higher value of radial location, and the heat transfer system is not in the same configuration described in the textbook. The negative values tell us that the heat flows radially inward. If we look at the derivation of rate equation for sphere, integration of the Fourier law of conduction involved the whole surface. This means we need to do additional step, so that we can make appropriate comparison, with values calculated for long cylinder and plane wall. This involves calculation of the heat flux, and the rate of heat transfer, when the heat transfer area is only 1 times 1 millimeter square. Let me review again what we have done so far. We place a chicken egg in an environment, in which the outer surface temperature of the eggshell at 100 degrees Celsius. And then we considered heat transfer process whereby the internal surface temperature is at 80 degrees Celsius, because we want to determine the rate of heat transfer, when we model the eggshell as a basic heat transfer system, i.e. plane wall, long cylinder, and sphere. We have difficulties to model the eggshell as long cylinder and plane wall. The clip shows the heat penetration volume for plane wall when the heat transfer area is only 1 times 1 millimeter square. The rectangular cylindrical hollows show the volumetric region that was used in the calculation. Next I show you the volumetric region, in which the heat flows through the eggshell. As you can see, the rate of heat transfer do not cover the whole surface of the eggshell, so when comparison was made with the plane wall, of course the rate through the cylinder is much higher but smaller than the sphere. This clip shows the heat transfer area approximated by the sphere. The calculation region involved the whole surface of the eggshell. We then understood that the integration of the Fourier law take difference region between one another. So we can conclude why the rate of heat transfer is different between the model of heat transfer system. The next issue that we want to explain is why there is a negative values for long cylinder and sphere. At the beginning, we place the origin of coordinate system for plane wall at x equals 0. Now we will change its location at 0.0215 meter from the hot surfaces. I rewrite the rate equation for the plane wall. This time I changed the xc and xh value to 0.02126 and 0.0215 meter respectively. The values of other properties remain unchanged. These values were placed in the Desmos scientific calculator, and the rate of heat transfer is negative 0.038 watts. So we can conclude that the origin of coordinate system is important because it will tell us the correct direction of heat flow, relative to the origin. To make a proper comparison, we will calculate the heat flux. The heat flux definition is shown in the clip. The property is defined by dividing the rate of heat transfer with the heat transfer area that the heat flow. I tabulated values of properties in a spreadsheet shown in the clip. I use the Excel application software. The yellow cells are the heat transfer area for long cylinder and sphere. The heat flux for the both are 37,790 and 37567 watts per square meter respectively. Next we compare the rate for heat transfer for all these basic geometries. The geometrical and thermal properties are about the same. We can see that the order of differences becomes smaller when we consider small heat transfer area. We expect the magnitude of heat transfer will much different when the heat transfer area become greater.